Am I audible?
So,
Yeah.
Yes, sir.
Yeah. So previous to the second increments, I think, yeah, we had started the fourth unit with sequential circuits. Okay. Basically, a CMOS implementation of sequential logic, and I'd asked you to come up with the AOI and OI circuit, a CMOS circuit for the clocked JK flip flop. Okay. And I'd asked that I can ask anyone to present and make your friends to understand. Okay, so anyone ready in doing so? Anyone is ready in doing so? The clocked and clocked JK flip flop. Okay, so even I had given the schematic of this. I mean the logic diagram. The clocked JK flip flop. So one using the NAND latch and another using the NOR latch. Yes. The moment if you are going with the NAND, it goes something like this. Okay. This is basically a latch that you have. So this is Q, this is Q bar. Okay. This is basically S bar and this is basically R bar. Yeah. And clock basically enable thing. The input stage you have a 3 input now. So this being the clock, this being the J, this being the K. The K will be having the Q bar, okay, and one of the other input for this three input NAND gate. 2 is again the 3 input NAND gate. 3 is the 3 input NAND gate, and this is what we have. Okay, so this is the Q. This is the Q bar. This is the clock. This is your JK flip flop using NAND latch. This is typically your LAN latch. Okay. Yes. Again, so this we constructed based on the SR flip flop, and this is using the NAND latch. The next is your NOR latch, right? So this is your yes, this is R, this is Q bar, this is Q, and here you add 3 input AND instead of 3 input NAND. So this is your J, this is your K. This is a kind of clock, and this is what you have, right? This is Q bar, this is Q. This is using the NOR latch. Yeah. And I had asked you people to come up with AOI as well as the OAI CMOS implementation. So, am I correct here? Am I correct? If you remember, this is what the assignment had people. Yes. So anyone is ready in presenting? Yeah. Sumuk. Yes, Sumuk. If you don't respond, you're absent immediately. Anubhav, note down.
Yes, sir.
Sumant. Sumant KS. Spandana. Okay, all three are absent now. Purvi.
Yes, sir.
Yeah, so can you just get me a AOI and OS CMOS implementation? So okay, before you go ahead, either of these two, okay, for which particular circuit you will come up with a AOI and for which particular circuit you will come up with OI implementation?
For the NOR AOI.
Okay, so for the NOR it is AOI, yeah.
And for the NAND it is OAI.
Okay, it is OI. So can you?
Yes, sir. Present.
Yeah, so you are done?
Yeah, just a minute.
Okay, okay. So you get me the OAI.
Okay.
Okay. Yes, Shruti. Shruti, are you there?
Yeah, sir.
Yeah. Can you get me the AOI circuit?
AOI, sir.
Yeah.
Yeah, I'll just scan and present, sir.
Yeah. I'll just stop.
Is it visible?
Yeah.
Yeah, the OAI, sir.
OAI. Okay, so your Q bar is J bar Q. Okay. I mean, you want to explain with the PMOS structure or the NMOS structure? Anubhav, those are leaving the meeting, just note out their names.
Okay, sir.
Yeah, immediately I want the names of this. Okay, so it is J bar. So what is the expression for the Q in terms of clock JK using NAND?
Yes, sir.
Okay, so Q is basically J bar plus Q plus
J
clock
bar
bar
plus
into.
Q plus clock bar into Q bar, the whole bar.
Okay. So have you got this J bar plus Q plus clock bar directly you got?
No, sir. First here, this thing,
NAND.
here you get NAND thing, and then.
That's what. So you are using a De Morgan's there and you are
Yeah.
Okay. 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 Yes, Shruti, go ahead now.
Okay, sir.
Yes, sir. I'll just present one. Give me a minute. Is it visible, sir?
Yeah, you have to zoom a little bit.
So this is the OAI for the NOR based SR latch.
Okay.
And this is OAI, sir. The same.
Okay. Okay. Good. Thank you. You can stop presenting. Yeah, so what they give, so for example, if I just go with this particular clock JK flip-flop using NOR latch, so straight away Q bar given as at this point, I call this as point A and this as point B. Okay, so point A typically is an AND of J clock Q bar, and point B is basically an AND of K clock Q. Okay, so this is Q and this is my Q bar. Then my Q bar, that is the NOR gate output, NOR gate 1, NOR gate 2, and AND gate 1 and AND gate 2. So Q bar is basically NOR 1 output Q bar, which is J times clock times Q bar plus Q whole bar. This is the NOR. Similarly, my Q, which is the NOR 2 output, okay, it's K times clock into Q ORed with Q bar entire complement. Okay, so you can see that this is in terms of and entire thing is OR and or inverter. Okay, so that's why this is AOI. Whether you take the complement or the uncomplement, it goes with the thing. Okay. So now for this, if I want to write the Cmos structure, okay, so it will be a simple thing. So that's what we'll try to do now. Just a minute. Yeah, so we want to go with this, right? Okay, so the CMOS implementation of clocked JK flip-flop using NOR logic. NOR logic in a sense, NOR latch. This is what. You should be very careful when you are asked with any question. Okay, so it should not be something like a random, you have to go with anyone. Okay. So we had Q bar as J times clock times Q bar, entire thing OR with Q complement, whereas Q, this is K times clock into Q plus Q bar whole bar. Okay. So I can go with these two expressions now. Okay, so if I want to go with this, so first I'll go with Q bar, then I'll go with Q. Okay, so one structure for Q bar and another structure for Q, whereas the outputs are being a feedback. So if I want to go with this, so I have, since J clock and Q bar, they are in terms of AND, they will be connected in series. So that is what this J is all about now. Okay, that's what is clock, and I'll just try to connect this Q bar, okay, in this fashion. Okay, just for making the circuit to look a little bit better. That's it. The way we represent should be the things. That's it. So now this J clock and Q bar is in parallel with this Q because it is odd now. This entire thing is now odd with this, means Q is a parallel aspect now. Okay. And this is what my Q is all about. And this is, you can see that this entire thing is now parallel with this one. Okay, so this is the NMOS structure. So similarly, we have to go for the PMOS structure with the opposite way. J, K, and J clock and Q bar connected in series means in PMOS they have to be connected in parallel. Okay, so this is my J. This is my Q bar. Okay, and this is my clock, and all these are parallel, and you can see that J Q bar clock is parallel, that is in should be in series with Q now. Okay, and this is my Q. Okay, so this is how I am just writing the circuit. This goes to my VDD, and this is my VSS that we have already there. Okay, and what is this point is basically now? Yes. Yes, what is this now? What is the output that I'm getting over here? Where the drain of P structure and drain of N structures, what is this? Is it Q bar or Q? Or is it an R? It is basically, it is Q bar. Okay, this is what. And that's what this Q bar, whatever we are writing, so this is going in, that's it. Okay, so that is another thing that is. This is with respect to the NOR 1 output. Okay, this is basically an AOI structure because you know what is AOI? AOI is basically the complement of sum of products. This we got the NOR 1 output. So now we'll be writing the NOR 2 output. Okay, NOR 1 output is basically Q bar. NOR 2 output is basically Q now. Okay. Similar structure we'll write, but in the opposite way. That's it. Okay. So I'm having here. So this is my K. This is my clock, and then I have the Q grounded, and K clock Q is ORed with Q bar. Okay, ORing means it's a parallel version, so I'll just go with, okay, this is what, this is also grounded. This is basically my Q bar. Yes, and this is Q, and then I have, for the Cmos structure, I have three things in parallel now. Okay. This is my clock, so that's why I can just short these two. Okay, all this parallel. So this is my K. Okay, and this is my Q, and now this entire thing, this is NAND, not basically, it's a PMOS. This is basically now the Q, and this is what will going as here. And this is Q bar, this is Q bar, and then this one. Okay, so now this Q bar will be going as one of the input of this, and this Q bar will be going as one of the input of this. Okay, and this is the complete structure of the CMOS implementation of clock JK flip-flop using the NOR logic. Typically, it's an AOI, which is nothing but what, sum of product, complement of sum of products. In a similar fashion, you can go ahead for constructing the OAI, just getting the what is your Q bar and Q expression in terms of complement of product of sum, where finally you arrive to the OAI structure. Hope this is fine. Yes. Hope this is fine. The CMOS implementation of the clock JK flip-flop. So we saw the CMOS implementation of the NOR and the NAND logic. Okay, and then we went for CMOS implementation of the clocked NOR and the NAND logic, latch basically. Then we went with that is what we call it as SR latch basically, and from SR we went for the JK, the clock JK, and that's what we got the AOI and the OAI circuit now. Oh, this is fine. Shall we move ahead? Yes, no?
Yes, sir.
Yes, sir.
Yes, sir. Okay, so now my simple question is, We saw simple latches of SR using NAND and NOR. We saw clocked SR and SR latch using NAND and NOR. Then we saw today the clocked JK latches using NAND and NOR logic. My question is, all these flip-flops, what all we have studied till today, are they level sensitive, or they are edge sensitive, or they are pulse sensitive? Fast. Level sensitive. Okay, so all are latches only now. What till now, what all we have studied, they are just latches for us. Okay, they are level sensitive, whether they are clocked or not clocked flip-flop, but they are latched. And for your JK flip-flop, it has to be clocked only. Okay, so this is what we have now. So now, having said and done, yes, next thing is, what is the problem in latches now? Okay, can anyone tell me what is the disadvantages of latch? No doubt they are level sensitive, I can understand, but still, what is the disadvantage? Yes, anyone? Fast.
Race around.
Race around. Race around in what? Race around in what? Race around in which particular latch, I'm asking?
D.
Yeah? Huh? I didn't hear properly. Is it race around in SR latch? Is it race around in JK latch? Yeah? Fast. So in which particular latch we are having this latch problem and the race around condition now?
Yes, sir.
SR. So you have a race around condition in SR. True? Race around condition you find only in the JK flip-flop for your kind information. Yes? Yeah, that is what. So race around condition is the problem or the drawback. You find it in the JK flip-flop. The clocked JK flip-flop, what I'm saying. Okay. So the clocked JK flip-flop, okay, whether it is NOR based or a NAND based, okay, flip-flop. Typically, when I say this flip-flop as a latch, then only this race around condition comes. Meaning, when both J and K are 1, that is logic high, logic 1 or high, logic high, whatever you say, okay. So output won't be stable, it will be unstable. Okay, output will be unstable, meaning neither it will be in a logic 0 nor it will be in a logic 1. It will be continuously varying between 0 and 1, and that's what we call it as something like a race around condition. For that, for example, if you want to just check what is really happening here is, suppose if I have a clock which is continuously going, I'll just take 1 or 2 minutes to explain this part. I know most of you have forgotten because of not understanding, forgotten because of the time, okay, lot many reasons. J and K. For example, J is 1 somewhere here and then it becomes 1. K from 5. After this it becomes kind of 1 year, okay. I'm interested in, this is edge trigger, whereas this is my level sensitive, okay. I have a differentiation between the edge and the level sensitive. Right now, since it is a latch, it is all about my level sensitive. Yes. Now, assuming Q previously is set to 0. Okay. Logic 1, 0, and this is logic 1. This is 0. The moment this clock comes, okay, the first clock comes. This is my first clock. This is my second. This is my third. Okay, this is what I have. The moment the first clock comes here, okay, J is 1, K is 0. So that's why my output will be set. It is simply a SR, it follows an SR flip flop, right? When J is equal to 1 means it is S is equal to 1, K is equal to 0 means it is R is equal to 0, S1 R0 means it has to set. So output goes from low to high. And you can see that for until clock is equal to 1, J is remaining 1, K is remaining 0. So that's why until this point, if I take this as T0, this is T1, since there is no change in J and K value for the first half of the clock cycle where clock is 1, my Q remains to be 1. It is in a set. This logic 1 is basically for me a set. Okay. Then when clock becomes 0 here, irrespective what is my J and what is my K, what should be my output Q? What should be my output Q now? When clock is 0, what happens to your latch? Is it enabled or disabled? Yeah? Fast. Fast. When clock is equal to 0, what happens to your latch? Whether it is enabled or disabled? Yes?
Disable.
Disabled, right? So when it is disabled, so when it is disabled means what will happen to my Q? What will happen to the output of that disabled latch? Fast. Previous output. So from T1 to T2, okay, even though my flip-flop is disabled, but it will follow the previous, right? So that's why this is what. And this is nothing but what the QN is all about. We are saying, okay, this is what. And once again, so second clock cycle is coming, and for that, clock is 1, the moment, okay? So this is what. Okay, I'll just take somewhere around a fraction of time here, okay? This is something like T2 plus delta, okay? T2 plus delta, I can see both J and K is 1, and also clock is 1 enabled. So my output Q, when J and K is equal to 1, my output Q n plus 1 should be the complement of previous. Okay, this is what the truth table says, right? So it will go from high to low. Okay, but you can see after T2 plus delta, since latch is a level sensitive, until my clock is 1, my flip-flop is enabled and it is sensitive to this clock. For the next at T2 plus delta, I can see J and K are still 1, 1. Again, my Qn plus 1 should become Qn bar. So from T2 plus delta next is the complement of the previous, that is T2, from T2 to T2 plus delta is 0. From T2 plus delta onwards it becomes 1 because it is some complement. Okay, and you can see that after some time, I'm just taking some random time here. Okay, don't ask me what really happens between T2 and T2 plus delta. Okay, I'm just going. Again, it will be keeping on doing the same thing until the clock finally becomes 0. Okay, something like this. And then if it is 1, it will retain in 1, or if it is 0, it will go to the 1. Okay, and this is what we can see that, okay, not desired output. Even though I'm getting output, but it is not the desired because it is not stable. It is either 0 or it is 1, and it keeps on doing that. Okay, so in order to overcome this, and this is what we call it as a race around condition. And this race around condition happens in the single clock cycle. Make sure that too when clock is 1, that is when the flip-flop is enabled. You can see that there is a continuous 0101 instability in the at the output when J and K are 1 in the clock JK flip-flop. And in order to overcome this race around condition, we will either use the master slave flip-flop, and that's what we are going to see next. Master slave flip-flop, which is basically a pulse trigger, or edge triggered flip-flop, okay, which is basically an edge trigger. Okay, so that's why we are going from clock to JK flip-flop, because it overcomes the problem of SR. That is, in SR, when both are 1-1, output is undesirable. In a sense, it is not the valid output. So we went with the modification in the circuit and we called that as JK flip-flop. We could get the output when both J and K are 1, but it is the complement version. And the moment I provide J and K continuously 1 when flip-flop is enabled for the clock is equal to 1, then I get this 10 10 10, that is a race around condition, right? Which is again unstable now. Output is fine, but it is unstable. And in order to overcome this unstable, that is a race around condition, we either go with master slave flip-flop or edge trigger. Predominantly, both gives the mechanism or the solution to overcome this race around condition. Okay? And that's what we are going to see in the next particular slide, that is master slave so we'll go from a clocked JK flip-flop to master slave JK flip-flop. Okay, again I can construct the master and slave JK flip-flop either by using a NAND or by using a NOR. Okay, but predominantly both has to give me the same output. Okay, so this is what we have. Yes, now we'll try to see the NOR based. Okay, the NOR based in this example. As an example, we'll go with the NOR based. Just why I always go with the NOR based now, most instead of going a NAND based? Can anyone tell me why I'm interested in going with the NOR based rather than the NAND based? Even both are same. Yes, any guesses or any reason why I'm using a NOR? In previous clock JK flip-flop also I used the NOR. Now also I'm going with the master slave JK flip-flop, NOR based. Any reason for me? Any reason?
Implementation.
Yeah, it is simple AOI implementation, because we are so much addicted to this sum of products, right? And complement of that is basically an AOI. Okay, so why I'm basically prefer an NOR based is because it is an AOI and or inverter, that is sum of products with the complement. Okay, so that's why I prefer that. Okay, so it is a simple structure again. Okay, so you can see that I will have two stages, one as a master and another as a slave. You can see what is slave and what is master. Okay, all these are a recap of your third semester, but it is useful for us in developing the Cmos circuit. Okay, because from now onwards you should be in a position to understand any logic can be implemented using your Cmos, and that's what the main agenda of this particular third and the fourth unit, right? Yes, so you have to know the implementation of the Cmos for any logic, whether it is a combination or sequential. Okay, so this is what we have. Now, can anyone tell me what is this? What is this part? The right side, that is NOR gate 1 and NOR gate 2, I have bifurcated, right? So what is the right part of this bifurcation? Fast.
Latch.
What latch? What
Unclocked.
latch? Huh?
Without clocked.
No, without SR latch. It is just an SR latch for me. Okay? Yes. And what is this now? What is entire thing right side to the big bifurcation that I have done now? Yes. What is this now? What is this entire thing now?
Clocked, sir.
Clocked SR. That's it. Okay, that's the difference. This is S. This is R. This is S. This is R. Okay. All of you are with me? Yes. This is SR latch. Simple. It is not clocked. This is now the clocked SR latch. Clocked SR latch using NOR logic or NOR based clock SR latch. Okay. This is one. And then I'll have one more here. Okay. Again, what is this? By right side to the bifurcation, that is, I'll just go with this as something like 3 and this is something like 4. What is the bifurcation to the right side we have in this?
SR latch.
It is again SR. This is SR latch. Okay. This is SR latch for me. So here also I'll just say something like Q bar. This is something like Q. Okay. Then, and what is the entire thing now I have? This is S, this is R. This is again the clocked SR latch. Yes. Now, how to convert this clocked SR latch now? Fast. Sorry, this is S. This is R. Yeah. Yeah, how to convert? So what we are doing is we'll try to ensure that this Q bar, the moment if I give this, so instead of S, it becomes now J. So then Q I am giving as one of the input for this NAND. Okay. This is Q bar and this is my Q. Instead of R, I call this as something like K. Hope this is fine. Yes? No? This is yes, this is R. Okay. And this, whatever the Q bar I am having, okay. So this will automatically go to this output and this as clock input. And there is a difference between the first stage clock and the second stage clock. There is a 180-degree phase shift. That is, when the first stage flip-flop is enabled, the second stage is disabled. And the first stage flip-flop, we call it as a master. And the second stage, we call it as something like a slave. Okay. That's it. So this is your JK flip-flop. Okay. That is the master slave JK flip-flop. Any complication in constructing? Nothing. So this part will just tell me this is an SR latch. This also tells me this is an SR latch for me. That's it. Okay. Depending upon what is that coming over here and here defines my output. Similarly, what is coming over here and here defines my first stage output. Okay. And this is AND gate 1, AND gate 2, AND gate 3, AND gate 4. The AND gate 1 and 2 are 3 input. The output of AND gate depends upon J, clock, and Q bar, and the output of second NAND gate depends upon the K, clock, and Q. Okay, and this is what. So when master is enabled, slave is disabled. So when master is enabled, the slave is disabled, and we are interested in the output of the slave now. Okay, so we are interested, so that's why I call this as QS bar, this as QS, this is QM, and this is QM bar. QM bar is equal to S of the second state, that is slave S. QM is the input or nothing but what the slave R, that's it. It's so simple. So when slave is disabled means its previous output. Okay, it will just QS1 plus 1 I will be taking. It will be just holding its previous. Okay, similarly QS will be holding its previous, QS plus 1, that's it. You can see that whenever master is enabled, by slave output is completely disabled. In other words, their output will be the previous, that's it. Any changes in the master's inputs doesn't affect my output, whether it is a clock or this one. Okay. Similarly, when master is disabled, slave will be enabled. Okay, and QS plus 1 will be simply QM plus 1, and QS will be simply QM, that's it. Whatever I am getting the input at this point and this point will be going to QS bar and QS, that's it. And any change in the output of slave doesn't affect the master because master is disabled. Okay, master is disabled, so my Q bar and Q, any changes in the master output which is acting, sorry, slave output which is acting as a one of the master input doesn't have any effect over there. Things goes with respect to the master slave. Okay, so just to conclude, I mean, you can write the Cmos structure of this. I'll try to write just a waveform. Okay, a simple waveform I'll write with respect to the clock. So you need to understand what really happens with the master and the slave. Yes. Okay, so clock 1 0 1 0 1 0 1 0 1 0 1. Okay, M means master enabled, S means slave enabled. Master enabled. So master enabled means automatically the slave will be disabled, and so vice versa it continues. MS, MS, MS. Okay, this is what. Then I have J, K, which are basically master input. Okay. Then I will be worried about the master output. At the same time, I am worried about the slave output. That's it. Okay. And the truth table remains still same because we are not changing any of the parameters. Okay. Truth table of the master slave JK flip flop or the clock JK flip flop remains the same. That is, when both J and K 0 0, output will be previous, 0 1 reset, 1 0 set, and 1 1 complement. That's it. Okay. So I'll just okay. So initially J will be 0, K will be 1, and this is what I'll try to write the thing now. Okay. Something like this. I'll go J with some complement of this. This will remain same. Okay. Assuming that QS is initially 0. Okay. And QS and QM follows each other with half cycle difference. I'll assume this also QM is 0. Okay. And this is my T0. And I have to have both here, right? Okay. Okay, now first I'll just go with what is my master. Master enabled here, J1 K0. My QM will be what? 1. And it will remain 1 because for entire clock is equal to 1. Again, it is level sensitive still. Okay. Later we'll see why what exactly this master slave is all about. Okay. So master flip flop, only the off portion I am taking, the left version. It is still 1 for continuous until the clock is 1. J is remaining 1 and this is 0. That's why QM is becoming 0. And when the clock is 0, master is disabled. That means irrespective of this, this will follow the previous. That's what it is, 1 year. Next, M is equal to 1. Still J is 1, K is 0. So it is still goes 1. And afterward it will remain 1 because irrespective of this, this will go still 1. And after that, master is becoming 0. Okay. Slave is becoming, master is 0. J is 0. K is 1. So this goes to 0 kind of thing. Okay. And it will remain 0 because in the next thing it will be something like this. Okay. So this is what we'll see. Similarly now, QS, since slave is disabled here, it will follow the previous. That's what I'm saying, this arrow mark. And when master is disabled, when slave is enabled, you can see that QM is 1. And obviously my QM bar should be 0. And that is what it will be propagating to the output, right? So this will follow with this now. So you can see that my QS will follow my master off ahead the clock cycle. Okay. So at T1, between T1, T2, my QS will be simply as QM, which is between T0 and T1. Okay. So it will simply follow this. And in the next case, when slave master is enabled, you can see that slave is disabled and it will follow the previous. And after that, once again, the slave is enabled and slave will follow the previous master, right? And this is what it will do. And since it is 1, it will remain 1 only. Yes. And after that, it will remain 1 because here it is disabled. This is what I mean by. Then after this, slave is enabled. You can see that master is going down here and it has to follow the previous. It is going down. This is what is happening. Okay, you can just analyze in the circuit also. Next, after the first, second, third, beginning of the fourth cycle when master is enabled, both J and K are 1, 1. Yes. Make sure J and K are 1, 1. I'm just ensuring. So here, my J is 1, K is 1. Okay. You can see that it's Q bar. Okay. It's Q bar and Q is not varying because this Q and Q bar are from the output. Is that clear? This is what important is all about. Okay. So it is not varying. So master enabled, both J and K are 1, 1. So what really happens here? It goes 1 here. Yes. And since there is no change happening there, so it will remain 1, 1 and 1. It will go. You can just analyze with respect to that. Okay. And it will go something like this. And it will, sorry, it remains there. And again, it is continuous means it will go something like this. And the same thing, what really happens with respect to this? The slave will follow the master. So you can see that whenever slave I am getting the output, the slave output is independent of this. It is nowhere depending on this. So that means my QS, even though it is level sensitive, make sure QS output, which is the slave output, even the flip-flop is level sensitive, my output is not changing with respect to J and K. Okay. Whereas in the clock JK, the moment flip-flop was enabled, my output was changing with respect to J and K. And you can see here, the moment when J and K are 1, 1, you can see the output. In one cycle it will be 0, in other cycle it will be 1, in next cycle it will be 0, in next cycle it will be 1. But for a given cycle, it will be stable. It will be either 0 or it will be 1. But for a consecutive cycles, it will go on with respect to 0, 1, 0, 1, 0, 1, 0, 1. And this is what we call it as what? What we call this condition as? Yes? What we call this condition as? It is a toggle. Toggle. Okay, toggle. And toggling, but here you can see that slave is following the, and we call it as a 1 catching and 0 catching. That means my slave is catching either 1 or it may be catching somewhere 0. Okay, we call it as 1s and 0s catching. Okay, so this is typically what is 1s and 0s catching, and what is toggling. Toggling is different. 1s catching is the slave output is following the master, but after half cycle late, right? That's what we mean by the catching. And the moment J and K are continuously 1 for the entire clock period, for the consecutive clock pulses, my output in one cycle it will be 0, in the next cycle it will be 1, and it will keep on doing the 0, 1, 0, 1, 0, 1, and that's what we mean by the toggling. Okay, 0s and 1s catching we find in master slave. We will never find 0s and 1s catching neither in the clock nor in the edge, for your kind information. 0s and 1s we catching we get only in the master slave flip flop. Along with that, we get even the toggling. And toggling when both J and K are 1, okay, the output, okay, in one cycle it will be 0, in another cycle it will be 1, again it will be 1 and 0, provided clock is continuously coming. Is that clear now? And this complete 1 will be there for one cycle. Next cycle it will be 0, in the next cycle it will be 1. It is not within a cycle this 1, 0, 1, 0. In one single cycle, if you find 1, 0, 1, 0, that is a race around condition. Okay, and that is how we could overcome the race around condition using the master slave. Okay, and the edge figure we can see in the next class. Any clarification till this point? We'll stop here. Yeah, any clarification?